Okay. Good evening to everyone, and it's also always a pleasure for me to be here and share with you guys this moment for the Lights in Frontier Physics. And let me thank the director for the opportunity to use this room for this activity of our PhD course. And as usual, I'm going immediately to leave the floor to one of our PhD students acting as a chairwoman in this case for the talk. Okay, this is Alice Barbon, cycle 39, and then ciao.
So, good afternoon, everyone. Let me welcome Professor Yamaguchi from the Center of Nuclear Study at the University of Tokyo. Today he's going to talk to us about the radioactive isotopes, beams, and stars. The professor obtained his PhD at the School of Science at the University of Tokyo in 2004, and he worked in laser spectroscopy of the antiprotonic atoms. Then he moved to the Nuclear Center study at the University of Tokyo as an assistant professor, starting to study nuclear astrophysics project using radioactive ion beams named GRIB. Since 2012, he is the group leader of the nuclear astrophysics group at CNS, and he is leading experimental project for nuclear astrophysics, nuclear clustering, and nuclear reaction. So, welcome.
Grazie mille, buonasera. Infatti vorrei sempre provare il mio italiano, ma non è molto bene, parlo in inglese. So I'm Yamaguchi, and so first I show you. So I feel some kind of sympathy to be here in Sicilia, and so I remember Professor Claudio Spitarelli was often showing this one, the similarity of Montagna Etna and Montagna Fuji in Japan, and the height is quite similar, and the shape is both beautiful, and also I want to say the food here is very nice to me. So these are all Japanese style, but neonato, riccio di mare, algae, and carne cavallo. In Japanese, we eat it cruda, and even botarga, and there's something like pizza. This is my hometown style. And anyway, I really like to be here, and I enjoy the food here every time. Okay, then as I heard there are many students here, so I want to start from some basic things, and for students, I often start from this one. So this is about diamonds, diamante, and do you know how diamonds made? And now we know carbon atoms can make diamonds. And the carbon atoms have high pressure and temperature. It needs high pressure and temperature. And it's like 5 times 10 to the 4 atmospheric pressure and 1000 Kelvin. We need this condition. And then it can make a crystal. And moreover, it needs some condition. So diamonds are not found everywhere. But we need some scheme. So it's made under the ground, deep under the ground. And there, it can have such pressure and temperature. And it can make some kind of rock called as kimberlite. And it contains some diamonds. But it must be transported quickly to the surface of the ground. This is important. Otherwise, it's broken up. And then this magma flow can transport this kimberlite on the surface of the ground, and then we can find diamonds here. So it's very difficult, actually. And you can see this diamond, but usually you see diamonds after cut, but it's a natural crystal shape of the diamond. I think it's very interesting. Okay, so this is a story about diamonds. But diamonds are made from carbon. So how are the carbon atoms made and placed on the Earth? This is our question. So nuclear astrophysics has this kind of question. Carbon atoms, how they are made. And so now in the modern nuclear astrophysics know this fact, a nuclear process to make a carbon atom from helium. And we need a very, very high density. It corresponds to 10 to the 9th atmospheric pressure and also very, very high temperature. So it's much more difficult. So how, where and when they are produced? This has been a question of us. So we are studying nuclear astrophysics to answer such questions. Okay. And another thing we know is that we have very many atoms on the surface of the Earth. And this is actually solar system. The abundance, elemental abundance in solar system. And so this is the lightest atom, hydrogen and helium. These are very abundant because sun composed of these atoms. And we can find all kinds of atoms on the Earth, from the lightest one to the heaviest one, uranium. But if you look at this carefully, these lithium, barium, boron, these are quite small amount. But next, carbon, nitrogen, oxygen, these are very abundant, and these are important for us because our body is constituted of these elements. And you may notice this zigzag pattern, and so some are more abundant than others, like iron or lead. Okay, so this is telling us something. And we know this from the spectroscopy of solar lights, analysis of meteorites, and abundant surface on the Earth. So all these information are combined, and we know this. And this was elemental abundance, but we also consider isotopic abundance. So I hope you know the atomic number 20 is calcium, and so this is a number of protons in this atom. But calcium has 40, 42, 43, 44, 46, 48. All these can be found on the Earth. And actually, these two are not stable, completely stable, but very long-lived. And it's a bit interesting because the lightest one, is calcium 40, and this is a dominant one. And the second highest abundance is for calcium 44. And so this is also a clue to understand how they were produced. And looking at this in the next one, scandium, then it's all scandium 48. Yeah, so this difference is also interesting to me. And so this is a challenge for us. Can this abundance be explained? And now we know, I don't know all these, all the people here know about nuclear physics or not, but so nuclides are not only stable ones, but also unstable ones. And stable ones we can find on the Earth, and mostly. And these central ones are stable nuclei. But we can produce also unstable nuclei. This is one keyword of this talk. And unstable nuclei, actually, they are much more than stable one. So according to the theory, this unstable nuclei or radioactive isotopes can be 8,000 or even more. And it's much more than a stable nuclei. And these unstable nuclei sometimes have more neutrons compared to the stable ones. And the others have less neutrons or more protons compared to the stable ones. So we may call them proton-rich or neutron-rich, or sometimes neutron deficient, because anyway, proton number is not very rich here. Anyway, so this is showing the combination of neutrons and protons, and for the radioactive isotopes, we have many things to study. This is showing that. Okay, then how it's related to the astrophysics. And in particular, we are using low energy Alpha beams, as I will talk later, and why it's needed for astrophysics. So I can answer like this. And so stellar nuclear reactions. Initially I said we need a high temperature. That's true. But converting it into energy, it's not so high compared to the accelerator energies. And low energy. And now I'm going to talk about this SERIB facility. And it it can produce radioactive isotopes with 1 to 10 MeV per nucleon. So this mega electron volt range, this is low energy for us. But this is actually in the sun, the ambient energy is even smaller, like kilo electron volt, or even less. And so, so some people think the energy should be higher and higher. Higher energy is better, but actually that's not true. Low energy is not bad energy, and rather suitable for nuclear astrophysics. And why we produce radioactive isotopes? They are not found on the Earth, but they exist in the universe, like the stars, exploding stars. And so we should study the role of these unstable nuclei in the stars. And so, yeah, that's why we are producing unstable nuclei. So we need low energy Alpha beams to understand the universe. And but it's very difficult. Unfortunately, we have much difficulties to study this. So why Alpha beam experiments are difficult? First of all, the beam intensity is very small, and astrophysical reactions often have small cross section. And I don't know if everybody knows cross section, but I will explain later. And typical Alpha beam intensity is 10 to the 5th ppm, so 10,000 per second. This is a typical radioactive beam intensity. So you may think it's not so small, but yeah, actually it's small, because for light ion, like hydrogen, helium, we can produce an intensity even higher than 10 to the 14th ppm. So you may think 5 and 14 not much different, but actually it's really different, because yeah, we can have a beam time for 1 hour for the light ion beam. then it should correspond to 100,000 years for radioactive beam if the intensity is like this. And this may not a problem for stars because they can survive. But for us, it's too long time. We cannot perform an experiment which takes many years. It's quite impossible for us. And also another difficulty is available nuclei. So RI beams, as I have shown, RI beams, there are 8,000 or more. Some are easy to produce, but some are not. And so intense RI beams are not available for all nuclei. And yes, and there's a method to produce RI beams very widely. It's called as projectile fragmentation. This can produce very many kinds of nuclei, regardless of the property of the atom, but basically at high energy. And it's not astrophysical energy. As I said, astrophysical energy is basically very low energy. I can call it as a challenge for our intelligence. So this is why it's difficult, but it's interesting. But there are also positive facts because radioactive isotope in stars are often important in high temperature, or I can say explosive phenomena. So in quiescent star burning, then there are not many RIs. They can decay out, but at high temperature, RI can be important. And in that case, the reaction cross-section is not too small. So yeah, it's not so pessimistic. And what if the cross-section is very small? So probability to make a reaction is very small, but involves very rare isotopes. Okay, so this is very difficult to study, extremely difficult to study. So we cannot measure it for the present technology, but that reaction shouldn't be relevant for the universe. So as far as we're concerned about the universe, we don't need to measure this. So yeah. And so there are several methods to produce this radioactive isotope as a beam. And just I categorize into several categories. And the first one is offline separation. And it's a kind of method that once it's produced and by some means, and then transport it to another place and use it as a beam. And but apparently you need a long lifetime for this one. So it's sometimes it's very powerful, but only available for long-lived radioactive ions, like barium-7, which has a half-life for 15 days. And there are online methods. So we produce it, and immediately we use it. And one very typical method is ISOL. And this is applicable for the RIs, typically lifetime larger than 10 milliseconds. And this can produce low energy, good quality beam suitable for astrophysics. But there's a limitation by the chemical property of ions. So we cannot produce every RI with this method, but still it's very useful. And another method is in-flight production and separation. And this can be applied for even shorter lifetime nuclei. And the first example of this method was fragmentation, projectile fragmentation. So it uses a high energy beam and by the collision, the nucleus is completely broken up and into small pieces. And in those small pieces, we can find some radioactive ions. So this is one way, but it's only for high energy. And the second one, direct reaction, actually, this is the one we are using. So I explain it from now. And we may use another fusion-fission reaction. But by some reaction, we can produce it and use it immediately. Okay, now I'm coming to the introduction of our device. It's called a C-RIB. And this is a low-energy RI beam separator of CNS. And it's located at RIBF. It's a recognition center, operated by recognition center in Japan, Wako City. And this shows the overview. And it can produce low-energy RI beams less than 10 MeV per nucleon by infrared method. And primary beam from the Abel cyclotron. So there's a cyclotron accelerator, and it accelerates a stable ion. And then it's transported here. And here we have some kind of gas target. We call it as primary target. And it's like hydrogen or deuterium or helium-3 or something. And then we separate RI beams by these magnets and the wind filter. The wind filter is a combination of the electric field and the magnetic field. And after this, the beam is purified and it's used for some measurements. And maybe I skip this, maybe you don't know. And so the production, the principle of production or the method of production is actually very simple. So we use stable heavy ion beam and we prepare target, and this is bombarded onto this target. And then with for many new particles, it just goes through without doing nothing. Just the energy is a bit degraded. But with a certain probability, unstable nuclei are produced by nuclear reactions. So for our case, for example, so these black ones are stable nuclei. And if we want carbon-10, we use this boron-10 beam. And we make a so-called PN reaction. So this is the conversion of the hydrogen to neutron. And then we can make carbon-10. This is radioactive. And so in this way, the RI beam can be created. And moreover, it has certain velocity, and the produced carbon-10 also going to the forward direction, and it looks like a beam already. So this is a principle of in-flight RI beam production. And by using this method, we produced all these nuclei. So blue ones are stable ones. So we didn't create it, but for the other ones, so we are good at producing low mass and this proton-rich side RI beams. And the advantage of our method is so all these reactions can have large cross-section at low energies, and we can, our intensity is quite good, like 10 to the 4th to 10 to the 6 ppb. And our maximum record is for this one, barium 7. For barium 7, once we produced 3 times 10 to the 8 ppm by the cryogenic hydrogen target. Yes. And this is our target system. So basically, this is just a gas contained in a box. It's here. And this has 2 main features. So this is liquid nitrogen cooled. And the liquid nitrogen is filled in this tank, and it directly touches the gas and cools it. And so by cooling it, we can also have the higher density. The target thickness can be higher, and then we can have more alloy beams. And also, this is a unique feature of our system. We can flow the target gas all through the system, so circulate around and around. And this is to have a better cooling efficiency. So too high heat on this target, it breaks the foil, entrance foil. And so we have to cool it. And so it helps help us to do that. And we can also avoid the target thickness reduction effect. This happens when the beam heat deposition is very high. And you can imagine the beam goes through here, and the gas along this track is how to say, it's heated up and going away from this track. This is this density reduction effect. And by circulating gas, we can reduce this effect significantly. And one a good thing for our group is we are collaborating with many groups all over the world. And so in Asia, Korea, China are strong collaborators, and in Europe, Italy is the strongest collaborator for us. Okay, then from now I want to talk about the physics. And first of all, why we are doing this experiment? What we can measure in experiments? So we study this reaction cross section, and we want the energy dependence. And this reaction cross section, I hope many of you know this. So this is some kind of probability, standard probability of the how reaction can likely to occur. And so if the cross section is higher, the reaction can occur frequently. And so we want this one. And so this cross section can be determined from the target thickness and number of beam particle, number of detected. First of all, we irradiated the beam on the target. And in a traditional experiment, it's quite thin target. And we put a detector and count how many reactions occurred in the target. And so we know target thickness, number of beam particle, number of detected particle here, and scattering angle and solid angle of the detector. How large is the detector? Then we can have a measure of the reaction. That is a cross section. And by changing the energy or angle, we can have the differential cross section. The dependence can be seen. This is also interesting to see. But as I said, the RI beam experiment is quite difficult. And so how to overcome this difficulty? in particular, the low intensity of the beam. I can show you 3 methods, and the first one is measure another reaction with higher cross-section and deduce the cross-section indirectly, and you may call it as indirect method. For example, there's a method called as ANC, measure another similar reaction and determine the coefficient relevant to this reaction. And the second one is Trojan horse method, and I will talk about it a bit later, but actually here you have many experts, and I'm a bit embarrassed to talk about this one in front of you. And we can also study the resonance properties by some measurements. If the resonant reaction is dominant, I will explain it later for this case. And second one, of course, we can make the target thicker. So it's I will introduce thick target method. And number 3, improves the detection efficiency. If the detection efficiency, we can detect more, we can cover more angles, which the efficiency is improved. And the recent trend is this active target measurement. And I will show you a little about this. And now I want to discuss on the thick target method. So in a traditional method, it's I may call it as thin target method. The target should be thin enough so that we can keep the target, so that we can have the good energy resolution. If the target is very thick, the energy of the beam changes in this target. And so the resolution gets worse. This is a point. But this is a thick target. So we prepare a very thick target, and the beam energy can change even in this target. So but the detected particle, from the reaction, this energy is telling you where in the target this reaction occurred, in principle. And so if it's used properly, thick target experiment can be equivalent to many thin target experiment at different energies. So this makes our measurement efficient. And this thick target method, actually it's very old. It's at least it's known since 1960s. The example is this paper, carbon-12 proton-proton scattering, but it's combined with the inverse kinematics. Inverse kinematics means, let's say, in the typical experiment, in the traditional experiment, the beam was lighter than the target. Beam nuclide was lighter than the target. But we can make a heavier beam, and for example, carbon-12, and the target is a lighter nuclide, in this case, alpha, helium nucleus. And by making this one, it is interesting paper by Russian group. And so the title of the paper was Effective Method of Study of Alpha Cluster States. So yeah, this is telling us it was initially found as an efficient method to study clustering. But anyway, so they demonstrated in the normal method, we get one, we make a measurement at one energy, and then change the accelerator energy, and then move onto the next point, and then make a measurement. So again and again. So it takes quite a lot of time. But with this TTIK method, as the target is thicker, you can measure this spectrum in a single run without changing the beam energy. So the target automatically changes the beam energy. So this is showing how powerful this TTIK method is. And so for us, it's also good for RI beam experiments because first of all, it's efficient, but also because the RI beam can be produced by infrared method. But for us, it's not easy to change the energy step by step. But by using this six-target method, the energy changes automatically in the target. And then also another thing is the beam can be completely stopped in the target. So we can scan at certain energy down to zero energy. And even the very forward angle, we can put a detector. And in the traditional method, the beam penetrates and the beam directly hits the detector. And usually the detector cannot tolerate with that. Too strong beam breaks the detector. But with the six-target method, the beam can be stopped in the target, and we can put the detector in front of the beam. Okay, so until here it was methodology, and from here I want to show you some examples of our achievements. And we are interested in this X-ray burster. So if you look at the universe, sometimes X-rays are coming. And this is the observation. This has a sharp rise and slow tail. And the scale, it depends on which X-ray burster, but in this case, it is decaying like a few tenths of seconds. So we can see this kind of profiles by the recent improvement of the X-ray observation. And it is considered that the X-ray burst has this kind of mechanism. And so it's from the binary star. And one of the star is a neutron star. And the other is still main sequence star. And then neutron star is very compact, but this main sequence star supplies some fuel. It's like hydrogen, and then it can temporarily make some kind of explosion, and it is observed as X-ray. Okay, and in this X-ray burst, according to the model calculation, it is said as the burning process running a little bit neutron-rich, proton-rich side, it becomes important. So these are stable nuclei we can find on the Earth. But in the X-ray bursts, this burning path goes through a bit proton-rich nuclei. But the problem is we don't know much about this one because they are radioactive. And we can produce it, but we don't know the reaction rate so much. And we believe these alpha P reactions become important at a high temperature, like 2 or 3 gigakelvin. And sometimes it's called as the alpha P process. And theorists say this alpha gamma, alpha p, so alpha-induced reactions can be important, but the experimental data is not sufficient even now. So this is one achievement by our collaboration. This is about the magnesium-22 alpha p reaction. This is this was proposed by Dr. Fujun at IMP, Lanzhou, China. And he was once a CNS postdoc, and we have been working together very well. Sorry, so you can see your names here. And this reaction is here, this magnesium-22 alpha p reaction. And according to theorist, this is Richard Seibert, he made a ranking which reaction has a high sensitivity to the right curve. And this is ranked as number 5. So this is telling experimentalists and which reaction should be studied more. And so this is 80 years ago. The reaction rate, this reaction was not known very well. And so there are evaluation of the reaction rate, how strong this reaction is. And one is using a model, statistical model calculation, so theory. And another is based on the experimental data of mirror nucleus. And anyway, you can see a large discrepancy between the evaluations. And you see this is 10 to the 10th, 10 to 0 minus 10. So this is logarithmic and very, very different. Okay, so almost simultaneously with us, the MSU group, Michigan, United States, are also working for this reaction. We didn't know, but they made the first direct measurement of magnesium-22 alpha p. So they produced magnesium-22 beam, but the intensity is not very fantastic, 900 CPS. So it shows how this measurement is tough. And they use active target, and so they obtained several data points, but still it's higher than the real astrophysical temperature. And they extrapolated their data down to the astrophysical temperature. But we are not sure this extrapolation is really reliable or not. So we took another approach, and what we did was to study resonances. And the nucleus has many excited states, and these can be observed as resonances. And if you have resonances, the reaction rate can be enhanced. So it's also important to know if there are resonances or not. And so, but we also don't know the resonances very much. And so we try to study these resonances. So this is in contrast to the direct measurement by MSU group. And the measurement was using aluminum-25 beam. And so this is not magnesium-22. I will tell you later. Aluminum-25 beam and 2 times 10 to the 5th ppс, 80% purity. And we studied elastic scattering with the hydrogen. And so this setup is not so complicated, rather simple. The beam is detected by this p-pack detector, and we put the target, polyethylene, and recoiled protons were detected by silicon detector telescopes. Yes, then we obtained this spectrum, and this is showing the resonances of the aluminum 25 plus P. And so this is like looking from the backwards of this reaction. Aluminum 25 is the product of this reaction. And by doing this one, we can see we identify several resonances as the energy just contributing to this reaction. So by using the parameters of observed resonances, we can evaluate the reaction rate. And we assume the reaction rate is dominated by these resonance reactions. And we think that's true. So our idea is if we know the resonances, we don't need to measure it directly. Yeah. At the end, we have this red curve, and MSU group was like this one. So at higher temperature or energy, it's a bit off, but at the relevant energy, actually, these two are quite similar. So by our work and MSU work, the reaction rate uncertainty was reduced significantly. So I think this was a success. And we also made a simulation of the light curve, X-ray light curve. And this is also by scientists in IMP, Rancho. So this is, we try to reproduce the observed light curve of one X-ray buster. And previously, people couldn't fit the tail very perfectly, but by introducing our new rate and adjusting the parameters, we obtained this red curve, which reproduces the observation quite well. So in this way, we can improve the model, and now it's very much refined, I think. But after that, this is another experiment at Argonne National Laboratory in the United States. And they said the previous MSU cross-section was too small by factor 3 or 4. And this is their new measurements. So still, we don't know. We are not very sure. So they compare red curve, the present measurement, Argonne, and MSU. And fortunately, we are in the middle. And so we still have such uncertainty, and maybe we need more experiments. Okay, so this is another milestone of our series of experiments, and but I think so. Livio is the expert, and so maybe you have a chance to listen to his talk, and so I want to explain it quite briefly. And so this was experiment in collaboration with Japan, Italy, Korea, China, UK, and Italian people's contribution is really essential for the success of this. And so maybe I don't go into detail, but this Big Bang nuclear synthesis is the first nuclear synthesis in the universe. And after the moment of the Big Bang, after 3 minutes, or it starts. And the present model predicts a certain amount of lithium-7. And this is a calculation. But from the observation, so this horizontal axis is a baryon density. So how much the early universe had matter. And so, and observations, this is the abundance of lithium-7 from the earliest observations. And this baryon density is determined from the so cosmic microwave measurement. So anyway, so ideally these three should be consistent, should be at 1 point. But there's a discrepancy of factor 3 or 4 between the observed abundance and the calculated abundance of lithium-7. So this is called as cosmological lithium problem. And so in this direction, we have performed the Trojan horse method experiment to study a barium-7 destruction process. We believe that this is well known, but still not perfect. And one key issue, this is similar to the previous linear experiment conducted by Livio and other colleagues. And one key issue was the barium-7 NP should be the strongest barium-7 destruction reaction. But actually it has two reactions, and one is NP0, the other is NP1. Then what's 0 and 1? So NP0 means lithium-7, produced lithium-7 is at the ground state. And for NP1, this lithium-7 is excited and it has higher energy. And in the previous evaluation, this was considered, but this seems to be missing. And so one key issue was, can their contributions evaluate separately? So we improved the energy resolution to separate the two with a Q value. And so this method, maybe it's no need to say it to you, but it's based on the old gradient of Troy. And so the essential problem of this difficulty of low energy measurement is this soldier, it's proton actually, cannot penetrate the barrier. This is Coulomb barrier of the nucleus because he doesn't have much power. So this soldier is put into the force. And this in our experiment, it's proton contained in the deuteron. And then this horse can be powerful enough to penetrate the barrier. And then the soldier can do his job. But at the same time, horse shouldn't work for this. So we have to confirm this is soldier's work. But anyway, in this way, we can know how soldier can work under this condition indirectly. So in our real experiment, we wanted to study barium-7 plus neutron reaction, but these two are both decaying into another particle. For this one, lithium-7, and for this one, proton. So usually it's difficult to use them for the experiment. And so this Trojan horse method also helps that. And yeah, so we measure 3-body reaction, barium-7 plus D, making PP lithium-7. And then this Feynman diagram can be decomposed into virtual reaction. This is what we want. And this is called as virtual decay. And this can be decomposed into two components. And by measuring this, we can deduce this one, assuming this is well known. So this is an essential point. And experimental setup was like this, also again in the same chamber. And the beam is coming from here and measured by p-pack detectors. It was barium 7 beam, 22 MeV. And here we placed a CD2 target. And after the reaction, for some events, it has resumed 7 pp, but spectator momentum is very small. So we measure this resume 7 and proton. In this way, we can identify the 3-body reaction. And this is a bit complicated, but the key issue was if we can separate NP0 and NP1. So as you can see, this is asymmetry. So this is P0, P0 should be here, and P1 should be here. And this asymmetry surely shows there's P1 component. And it's difficult to separate the events one by one, but we can still evaluate this, how much their P1 component is. And by doing this separation, we obtained an NP1 reaction. And this is for the first time to obtain the cross-section experimentally at this big bang nuclear synthesis energy region. And we, using this, we applied the new reaction rate. It's enhanced from the previous one. And it's like, it depends on the energy, but it can be over 10%. And this NP1 data predicted that the lithium-7 abundance can be 10 to 15% reduced at maximum. But the original discrepancy was factor 3 or 4. So we wanted 70% reduction. So it's too small. So, but it's not a solution for this problem, but we are approaching to the solution. So we call it as a partial solution of this problem. Do I have time? It's okay. As you wish. Okay, yes. Then I try to finish. And I talked about the thick target method in inverse schematics, but there's one disadvantage. So if there are two similar reactions, we cannot tell which is which, and because we only measure the outcoming particle. And to solve this problem, we can do gamma ray detection to identify the channel, or using an active target. And this is an active target we used before. And so this is a kind of TPC, time projection chamber. It's kind of detector, three-dimensional detector. But it's also a target because it contains helium gas. So in principle, the reaction in this TPC can be detected at that position, and we can identify the reaction vertex. And using an active target, we recently performed this oxygen-14 alpha P reaction measurement. And this was Texas active target developed at Texas A&M. And maybe I don't go into this, but they brought the Texas active target to sea level. So they are coming in big boxes. And this is how it looks like. So this is kind of chamber, and we put some bias in this direction. And so we used it for the measurement. And maybe the final result, okay, so it's still under analysis, and I hope we can show you final result quite soon. And it's not astrophysics, but another topic of theory is this strange cluster state. It's called as linear chain cluster state. So usually the nucleus is circular, like a circular shape. But for some specific nucleus, it can have such a strange structure. It has alpha particles aligned in a line. And so this was predicted by theorists. The oldest one was really, really old, but recent prediction for the carbon-14 was like this in 2010. And we made some resonance scattering measurement, and we identified some indication of this linear chain state. But this must be studied more. We don't think this is a very firm evidence. And so we are studying like this. Okay, that's it. So CRV is our facility, and it can produce low energy RY beams by infrared method. And it's very useful for the astrophysical reactions because it's low energy. And I introduced recent barium 7 and magnesium 22 experiment. And this lower mass oxygen 14, nitrogen 13 alpha reaction were also measured recently. Yes, and I'm very glad to collaborate with foreign researchers. So we welcome new collaborators, new ideas. So please contact me if you have any idea. Yeah, thanks so much.